What's up, gangsters? This is going to be a super nerdy 3D printing video. And I, once again, have to warn you that this is going to apply to like 3 of you. Because this is specifically about a defect that's common when you're trying to print at 10 micron layer thicknesses. Which, I know some of you are like, why would I ever want to do that? Well, it's a thing for scale modelers when we are trying to print really detailed parts, or we want a really good surface finish. Yeah, 10 microns, it's a thing, it happens. Definitely not very often, but when you do it, you want your parts to be right. And this is a video about a very common problem and how to solve it. Okay, so the thing that we're talking about is something that some of my friends and I have been calling the accordion effect, because honestly, we don't really know what else to call it. And here's why, okay? This is what a part should look like. And you can see the height that these cylindrical features protrude from this base. And this is printed at 50 microns. Here's the same part printed at 10 microns, and you can immediately see the problem. The cylindrical features seem to be almost submerged, and the base is quite a bit thicker. But when you put a measuring stick on these, the total height of the cylindrical features is the same, and it's correct. And so that's why we're kind of calling it the accordion effect, because it's almost like these lower layers have been pulled up to a gradually lessening degree until somewhere before the absolute top surface of the part is printed. So that's the issue. Now, before we get to exactly what's causing it and how to solve it, let me see if I can define some terms that are important. All right. First, let's talk about elephant's foot. Okay. Elephant's foot is one that you'll hear a lot, and it typically refers to when you're looking at a part, and let's say that this is the surface of the build plate. Not very flat. Hopefully yours is flatter than that. And the part is printed directly on it, or maybe it's the base of the part, your supports, and it looks like this when you look at it from the side, where instead of the sides of the part being straight up and down, they're bigger at the bottom. And you can see it in a real world example on parts like this, like these test coupons that I run to dial in my, sorry, I'm bumping the camera again, of course. These are test coupons that I use to dial in my settings for any given resin. This one is made by Photonsters, and I like it because it's got a lot of good detail, and because it's so thin, it prints pretty quickly. But this one has a problem, all right? You can see it. There's multiple outside edges, and this one that's sticking out the farthest is not supposed to be there. It's supposed to look like this. Okay, here's one right here that, even though it looks like a potato chip, the outside edge is correct. There's only supposed to be one edge, not 2. All right, you can see that extra sort of fringe around the sides. okay? That's elephant's foot. Sometimes people mistake a extra thickness in the base, like you see with this part, as elephant's foot. But elephant's foot is only an XY error. It means basically that the dimension of the layer in the X and Y direction is larger than it's supposed to be, and that's what results in it being wider at the base, okay? Now, there are two potential causes for elephant's foot. The first one is often given as the only cause for elephant's foot, but it's not really. All right, and it's called bloom, okay? Now, let's imagine that you have a single pixel in your, that's being printed in your masking SLA resin printer, like my Elegoo Mars 4 Ultra, Elegoo Saturns, Frozens, Anycubics. All of these machines work on the same principle of masking and revealing pixels in a screen to either allow or not allow the UV light that cures the resin to pass through to the resin. And the pixels, in general, are little tiny squares. But the reality is that you get some energy bleed all the way around if this was just a single pixel. These edges are not magic impermeable barriers, okay? If you think about the fact that if this is your build plate on top where it should be, and obviously not as flat as it should be, and this is the surface of the FEP in your vat, and the screen is down here with the light, all right? And you shine UV light into the resin here, and your profile of your part is supposed to be just like this. And imagine that this is one layer. And that's what the profile is supposed to be. Some of this UV energy there's a little space here. Even if it's only one layer thickness, if that's 10 microns or 30 or 50 or whatever, there's a little space here where this is solid, fully cured resin, and it's supposed to be contained in that volume, but there's a little bit of bleed here, okay, on both sides. And when there's enough of that energy bleed, you get this oversized condition around the edges of that profile. And it can happen at any exposure level, but the reason that you see it the most at the bottom of a part is because you're typically using burn layers to make sure that the part sticks to the build plate. And so instead of exposing for, say, 3 seconds, you're exposing for 30 seconds. And so you've got a lot longer for this energy bleed to take place, and so you get more of it out here, and it's actually noticeable. All right? Now, bloom is a term that's actually been around forever. Back in the day when I was actually working in 3D printing right after I went to grad school for mechanical engineering at Texas A&M, I was working for DTM, and DTM was the original makers of SLS, selective laser sintering machines. And those machines operated by using a laser beam to selectively melt nylon powder or any other thermoplastic powder that that could be melted. But 3D Systems was also producing machines at that time, and those were the original SLA machines. They were the forerunners of things like my Elegoo Mars 4 Ultra, but they also used lasers. And bloom was a term that we invented to describe the fact that a laser beam, rather than a very sharp-edged circle, was actually more like an airbrush, and you had this little bit of overspray around it, if you will. And so if you were running the laser beam in such a way that this side of it was supposed to correspond to the edge of your part, you might get a little bit of overcure out here, and the part would be a little bit too large. That's why I often say that, as a rule, 3D printed parts are going to be a little bigger than they should be. Or holes are going to be a little smaller. It's all the same thing. At any rate, we even had a parameter on the SLS machines called beam offset that would allow us to scoot the beam over by a specific amount where it was running around the perimeter of the part, such that this overspray, if you want to call it that, actually was happening in the right place to make the outside of the part be the size that it should be. And that's where bloom comes from. And it is, and that's the only thing that bloom correctly refers to. Unfortunately, in the 3D printing community, we've seen bloom come to be described as any unusual growth of features on any given layer. Like, for example, this part right here has a bit of a defect right there that runs across the face. That line should not be there. And there are people who will refer to that as being caused by bloom, and that's just simply not the case. You can see them down here as well. All right. And I mean, yeah, okay, bloom is layers sticking out from where they should be, I guess. And if you want to call any situation like that bloom, all right. But I don't. I'm an engineer. I like for nomenclature to apply to specific things because often the cure is dependent on exactly how the effect is caused. And that's the case here, all right? Because with actual bloom, where you've got energy bleed, you've got a consistent amount of offset that goes all the way around the pixel or the slice, you know, whatever you want to call it. If it's 0.5 millimeters, it's going to be that all the way around, no matter how big the area of the slice is. It's a constant. Okay, and the way that you deal with that is by an offset. So just like we had the beam offset parameter on the SLS machines, if you look like, for example, in Lychee Slicer, there's a parameter called compensation. And you can apply it to both burn layers and regular layers. And all it does is take your profile. So if your profile is a triangle, all it does is take the profile and shrink it a little bit to compensate for that oversized condition. And that's how I eliminated it on these test coupons. Basically, it's just shrinking those first burn layers by, I think I've got it set at 0.5 millimeters. And, you know, you might end up with a little bit of a chamfer underneath, like is the case on this part. But that's not a big deal because that's just the base. Doesn't really affect the way that it looks. And it actually makes it easier to get it off the plate because your knife can go underneath the part a little bit easier. So that's bloom, and that's how you compensate for it. So if this issue here isn't bloom, then what is it? And what does that have to do with this defect that we're talking about right here, because they would seem to be completely different things. All right. So now we get to the third term, and this is a term that I kind of am trying to push, called squish. All right. And squish is exactly what it sounds like. All right. Imagine that your build plate here, all right, and your screen or your FEP, all right. Now, you know that all around this is liquid resin, okay? And let's just deal with the very first layer before anything else has been printed. The plate is coming down, and when it does that, all of the liquid resin that's between the plate and the film has to go out here. It has to escape until the plate stops at whatever layer thickness you are looking for. All right. Now, if you've got a profile, all right, that's supposed to be right here like this, all right, and you lower the plate and you're squishing the resin out from between the profile and the film, and the light comes on before you're finished squishing or squeezing this resin out, and the resin is still moving, what's going to happen? It's going to cure out here around the edges of the part. And that's part of what's happening here. It's really kind of two effects at the same time, and that's why that extra edge there is so big. All right, so let me say this again. What's happening here with squish is that the resin is still flowing when the light comes on, and there's a sort of a deceleration process. The resin doesn't stop moving fully before the light goes back off, and you get a little bit of extra that's being squished out to the sides, and that gets cured in the process. All right. And this too has a very specific way of handling it. All right. And that is with the wait to print parameter. That's what it's called in Lychee. I think in Cheetahbox, maybe it's called light off delay, which is a little bit confusing to me because you'd think that it would be light on delay, because what it amounts to is that basically you're going to let the plate come all the way down and stop, and you're going to take a beat before you turn the light on. You're going to wait to print. And the default for that parameter is 0. Printer lowers the plate, zzz, stop, light on immediately. And with the resin is still flowing, you have this issue of extra cure that goes outside the boundaries of the profile. So instead, you go the build plate comes down, zzz, we wait for however long we want to, then we turn the light on. And wait to print can be set to anything, but typical values for normal layers tend to be in the 1 to 3 seconds range. I have mine set to 3 seconds, and that works pretty good. It completely solved some of that sort of growth effect, the squish effect, on most of my parts. But obviously not all of my parts. And that's because there's more going on here than just the effect that we're talking about. This is also, if you look at the back side of this, where there's a sudden layer change. And that's also the difference between squish and bloom. The amount of squish that you get depends on the size of the cross section, because you've got more resin that has to be fully displaced with a larger cross section, and therefore you get a greater effect. And I understand that if you're looking at this, you're like, wait a minute, Patterson, this is exactly what you're talking about. You've got a sudden change of layer thickness of cross section size there, and that's coincident with this problem on the front. And yes, I clearly don't have it completely solved, but I've run very long wait to print times on these parts, and I still get the effect. And the bottom line is that this is just, this is not too much different from injection molding, where you have a sudden change in cross-section size. You can have different rates of shrinkage, and you can get effects like this. And there's a certain point where you're probably just better off, honestly, to stop chasing it with parameters and just utilize the sand command and deal with it manually. Anyway, the point is that wait to print is your friend. Pretty much everybody is going to benefit from adding a little bit of wait to print in their parameters. Okay, I know this is a lot of very long and tedious explanation. I apologize. It kind of is what it is when you get into these things, and yeah, just trying to get through it as best I can. But let's see if we can't get to the bottom of this and wrap it up. All right, so we've talked about these terms, elephant foot, and the fact that it's really not what's happening here, okay? It's a thing, but it would really only affect the very bottom of this part, and you can see that I've got the compensation turned on, and that's why I've got that little bit of a bevel there. Here's the other thing, and this goes to blooming as well. You'll hear people talk about vertical bloom. And I just want to point out, this should be obvious, but if we're talking about resin that's constrained between the build plate and the film, as it is when you're printing a layer, there's no way for it to grow vertically. It's fully constrained, it's trapped. There's no way to gather up new material because there's just no space. It's not there. It's not the same as when you have liquid on the sides of your profile here, and energy can reach that, and it can cure. So vertical bloom, as long as we're talking about stuff that's between the plate and the film, or between the last printed layer of the part and the film, you're not gonna get vertical bloom. Obviously, if you have parts with overhangs, you can get some bloom on the bottom or some droop, whatever it is. Like, for example, the bottom of the upper windowsill right there. When I take the supports off of it, it's a little bit, it's not quite straight because it's unsupported. So you could call that vertical bloom, I suppose. But point being is that what we're dealing with here with this over thickness of parts is not elephant's foot or bloom. All right. So we talked about bloom. We talked about the fact that that's a term that's been around for 30 years or more, 40 years. A lot of people don't realize that SLA machines were developed in the mid-'80s, and I was working with the first SLS machines in the early 90s. And we were talking about bloom back then. So it's been around forever, long before these masking SLA printers and their specific mode of operation was even thought about. And we also know that bloom is not going to happen vertically. So this is not bloom, okay? Not bloom, all right? This is entirely an issue of squish. And let me explain why. All right, so what you have to keep in mind is that as the build plate comes down and you are attempting to displace resin from underneath the part or the plate, that you're going to have a certain amount of force, okay? The build plate is coming down like this, and it's pushing on the resin, and the resin is pushing back, and you have some amount of force F, all right? And as it turns out, as your layer thickness decreases, that force increases. There's even a guy who's done a pretty cool blog, and he's actually put some potentiometers and some other circuitry on his printer so that he could measure the force in the build plate arm, and he's found that it kind of looks like this. If your layer thickness is decreasing as you go from left to right, that it kind of, that the force curve kind of goes like this, and then when you go from even from 20 to 10, it just shoots way up. There's a dramatic increase in the amount of force happening between the resin and the build plate, okay? Now, the next thing you should realize is that we're talking about pounds per square inch or newtons per square centimeter, whatever you want to call it. And so surface area plays a part, okay? And as the plate comes down and you're trying to burn your first few layers, now you're trying to push this entire plate, and you're dealing with the entire cross section of the build plate, and you've got to force resin out from underneath that thing and make it flow out of, around the edges here. This is the worst possible case. And that very first burn layer, if you're printing at 10 microns, I can't even talk today. If you're printing at 10 microns, your first burn layer is super, super thin. And so you've got the worst possible case where you've got this entire surface area and the least amount of distance between the surface of the plate and the screen. And so your forces are going to be really high. And if you noticed when I showed the picture of a lychee, my wait to print times are 10 times longer on my burn layers. I've got 30 seconds of wait to print on my burn layers and only 3 seconds on my regular layers. And that's because of the fact that I have so much cross section and I need a lot more time for everything to flow out and stop moving before I turn the light on, okay? But that doesn't solve the problem completely. And this is a thing that's really easy to test for yourself. I would encourage you to try this with a similar part. I've had 3 different guys run this same set of parts on 3 different machines using 3 different resins. I've run it on my Mars 4 Ultra. My buddy John Colasante has run it on his Saturn 4 Ultra. And our buddy Tom Annis has run it on his Anycube, or on his Frozen Sonic Mini 8K. Now he normally gets around it by having the fact that the Sonic Mini lets you have 2 different layer thicknesses, and so he can start at 50 and then switch to 10 after the burn layers. But Elegoo doesn't let us do that, so I asked him to run these parts at a constant 10 microns, and he got identical results to mine. His parts looked exactly like this. And I've also run various other parts, okay? I ran this little part, and when you measure these out, you can see the same issue. Not quite as bad, but the issue's the same. And I ran this where this one was up on supports, and this one was built directly on the plate. Because a lot of people ask, well, does this issue go away as you get higher up in the build? And does it matter if your part is on supports? And the answer is yes and no, and I'll explain why here in a second. Here's another part that I ran. Okay, this part I ran like this, printed it directly on the plate and 5 millimeters up on supports. And I did this one to satisfy myself that the size of these little cross sections didn't really matter. And the interesting thing was, when I started to really kind of get clued in, was that neither this one or the one that was up on supports showed any of the effect at all. All of the vertical distances were absolutely correct on these little parts. So what's going on? Why am I getting it on all of these, a little bit on these, absolutely getting it on this part right here when I run that, absolutely getting it at the top of these little dashboard parts where some of those surface details start to get a little bit submerged, and I had to make them comically tall to make them stick out far enough. I mean, this part is like 25 millimeters tall, and it's up on supports, and I'm still getting the issue up here at the top. All right, so here's what it comes down to. It is absolutely, okay, now actually before I say this, let me back up to the fact that I've also been talking about this problem with some guys in the Lychee Discord. Derek, who does the really good videos for Lychee, and a couple of other guys, and everybody has seen this issue. This is a common issue. Most people, though, aren't running at 10 microns, and so it's not really a problem. They don't really see it that much. And these conversations with these guys also helped me get finally dialed into what is going on here. All right, and it all comes down to force as a result, as a function of surface area. Okay, so let me go back to my little cartoons of these of our printers. All right, for the most part, these printers are all built, honestly, kind of flimsy. Like if you compared them to something like a machine tool, like a Bridgeport mill or a big lathe or something that's built out of cast iron. These machines are not perfectly rigid. When you have this force right here pushing up against the build plate, you're not really going to get any flex of the plate itself, or of the build plate arm, or of the rails. But because the rails are basically just screwed into this sheet metal base, you are definitely going to get a bending moment down here at the bottom. All right. It is also possible, everybody seems to agree, that we might be seeing a little bit of flex in the screen as well. Again, because keep in mind that this force goes up dramatically when you get to these really thin layers. So who knows which it is, whether it's the screen bending and flexing, or whether it's the this whole part of the structure flexing. Who knows what it is? But the bottom line is that when you are smashing the resin clear down to 10 microns, you are exercising a lot of force on that thing, and you've got a situation where, all right, if this is the build plate, and you've got a part right here, and you've got a 10 micron distance between the previously printed layer of the part and the screen, that when you're pushing against this screen, pushing against this structure with all of this force, that you've got more than 10 microns right here. Okay, let me say that again. This is nominally supposed to be 10 microns because that's what you're setting it at, but it's more than 10 microns. How much more? We don't know. But the fact is, like on these parts right here, the entire base is twice as thick as it's supposed to be. And so even if you're only now looking at 20 microns as opposed to 10, every single one of those layers twice as thick as it needs to be, you've got the bottom of this part being 4 millimeters thick instead of 2 millimeters thick. And again, the more surface area you have, the more your total force, and the greater the issue. So that's why I have so much weight to print time when it's just the build plate, all right? And I thought that was good enough. But the fact is that even as you go further up in the build, if you've got sufficient surface area, you will still have this problem. And even more weight to print is one possible solution. Okay, I did that. I changed my weight to print from 3 seconds on the regular layers to 30 seconds, and this is what I got. It's not perfect. This is 2.8 millimeters thick as opposed to 4, so it's still not correct. The tops of these surfaces are. So at least I knew I was headed in the right direction. But here's the thing. When I printed all of these parts, I had them arranged like this on the build plate. I had all 3 parts on there at once, and each of this one is half the size of the big one, and this little one is half the size of the middle one. They were always arranged like this, and so I always had the same amount of surface area. And one of the guys in the Discord chat said, well, hey, why don't you just run the smallest one and see what happens? And here it is. I didn't change anything other than deleting the 2 larger parts, and that is how the smallest part looks, and you can see it's absolutely perfect. So that, again, is still with 30 seconds of wait to print, and it got me down to exactly what I needed. But that's still a pretty long wait time. I don't know if I could decrease it. You know, I mean, if you add 30 seconds per layer, it's not too bad on this part. It's about an hour and a half to print that. But if you've got something that's as tall as this thing right here, that's about 2,000 layers at 10 microns. Yeah, even with only 30 seconds added to every layer, it's going to be an all-nighter, which may not be a big deal. I personally don't care. But, you know, still not the best possible solution. So I thought, all right, well, I wonder if, since what we're dealing with is resin that's being trapped in here, and it might even be that we have like this sort of bubble where, like, if this is the bottom of the build plate and you've got a part here and the screen is deforming like this, that you've got a lot more resin, relatively anyway, underneath here, and you've got this little thin gap where it needs, you know, wants to escape. And it's almost like a hydraulic valve situation where you've got this almost incompressible fluid and it's trying to escape out of this very thin gap, and it's just going to take a really long time. I mean, you know, maybe I think if you just waited long enough that eventually everything would settle down, the machine would come back to square, and your layer would actually be 10 microns thick. But who wants, I mean, how long is long enough? And who wants to add 60 seconds per layer to every print? So I thought, well, maybe it just needs someplace to go. So, yep, I just drilled a damn big hole in the middle of this plate to see if that would help. And I ran this build, and it helped almost none at all. these were about 1/2 millimeter to the better, but still not good enough. And I know some of you guys are going, oh, well, you ruined the plate. Yeah, well, not really. I mean, it still prints just fine. I just, can't put anything right there in the middle. And I actually, as I showed you, have 2 plates. And I hate this one. This is the one that came with the machine. And for some reason, it always sticks on the build plate arm. There's something inside there that makes it bind, and I've actually reached in there and removed a little bit of material, and I haven't got it figured out yet. But anyway, yeah, I don't even care. I hate this plate. I don't use it unless I have to, and they're only like 35 bucks. So anyway, I think that this idea has some merit for 2 reasons. Because you absolutely are giving the fluid another outlet that's better than just around the edge. But it just may not be enough. And the second reason is because this idea is used on, I think it may be the Frozen, maybe their the Revo, I'm not sure. One of those machines has the entire build plate perforated. And I guess that base layers still stick to it enough anyway. I'm really tempted to just perforate this whole plate and see how that goes. Who knows, maybe I will. But point being is that I think it's a sound concept. It's just that it wasn't enough in this case to solve the problem, because it really does come down to surface area. That's been proven to me over and over again. So once you get past dealing with the entire surface area of the plate, which really you should be by the 2nd, 3rd, certainly the 4th and 5th burn layers, now you're only dealing with the cross-sectional area of the part itself. And you may be able to affect that and minimize the surface area by orientation. I mean, really, as a rule, minimum cross-sectional area should be one of your goals when you're orienting parts anyway. But you can't always do that. You can't always design around it. Like in this case, this is the best orientation for this part. And even if I hollowed it out at some point, I've got to come back to a full cross section for the top part of the dash. So I can't really orient or design my way out of it in all cases, but what I can do is just print fewer parts. I have a tendency to load the plate up just because that's more efficient, especially at 10 microns, and I want to get as much stuff done as possible. And on these parts, I had 4 of them on there because I tend to print extras, always, because you just never know, when you're going to drop one or you're going to somehow screw it up or whatever, or you're just printing a lot of parts so that you can test out your engineering design. So the real simplest answer of all is to just print fewer parts. If you've got a really critical part and you have to print it at 10 microns, one at a time. It is what it is. The other thing that might help, I don't know this, I haven't tested it, is if you put your part as close to the back center of the plate as possible, because that's where the leverage is going to be the lowest and you'll get the least amount of flex in the machine, at least in theory, whether it's the structure or the screen itself. So there's, different ways that you can approach it, but there's no single necessarily definitive thing that you're going to do, like just changing one parameter and going on about your business. Okay, so there you go. I warned you, yep, super nerdy, super long, super detailed, as always, but that's the way it goes when you get into these sorts of engineering kind of problems. You just got to work your way through it. And I know that if you're like me and you've printed parts like that little dashboard part that I showed you, and you've been frustrated because you're like, man, that detail's not sticking out far enough to paint it easily. You know, and you have to go back and modify your design, or you can't figure out what the problem is. I mean, you understand the frustration. And so it's good to have a solution for that, and hopefully, you know, this was worth the time spent to get there. So, at any rate, I'll stop rattling on, and yeah, as always, I appreciate you watching. Much love.